today we will be finishing module 3, and as is typically done, I will be doing some practice problems. Now in module 3 we talked about basically about vector integration, and then we talked about some basic operations involving matrices and determinants. Okay. In these practice problems I will be focusing on vector integration. Okay, and matrix operations and determinants and all will be part of the module 4 also. So there we will take up practice problems on the matrix operations and determinants. Okay, so I will just write down a few problems that we will work out today. Okay, so the first problem has to deal with line integrals. Okay, so what you have to do is to calculate work done by f of x y. So the f of x y is a force, okay, in displacing a particle from A to B along two paths C1 and C2, which will be shown in the figure. I will just show you the paths. Okay, the paths are shown here. So this is the x axis, this is the y axis, and you have a point 1 0 and the point B is -1 0, and you have two paths going from A to B. The path C1 is C1, and the path C2 goes right along the x axis from A to B. So this is point A, this is point B. Okay. So what you have to do is to calculate the work done, and there are two forms of the forces when f of x y is. So in the first case I take f of x y is equal to 3 x y minus 1 into I hat plus 3 by 2 x square plus 4 y square into j hat, and in the second case the force is given by xy times I minus x square times j. Okay. So this is the statement of the problem, and I just want you to understand what we are trying to do in this problem. So the problem is you are taking this particle from A to B, and you are taking it along two different paths. This is C1, which is along a circle of unit radius, and C2, which goes right along the x axis. Okay. So just to emphasize, this radius equal to 1, radius equal to 1. So there are two possible paths going from A to B, and I am giving two possible forces. Okay. So for each force you calculate the work done along each path. Okay, work done when the particle is moved along each path. To solve this, let's take the first force. So the solution, I will write it in red. Solution. Okay. So f. So the first case, f is equal to 3 x y minus 1 times I plus 3 by 2 x square plus 4 y square into j. Okay. So the first term 3xy minus 1 is the x component of the force, and the second term 3x square plus 3 by 2 x square plus 4y square is the y component of the force. Okay. So that is just what we had here. Okay. Now, the first thing you can do is to check for path independence. Path dependence. Okay. And to do that, you take the derivative of the x component of the force with respect to y. So, dou Fx by dou y is equal to, so the x component of the force is 3xy minus 1. So, the derivative with respect to y will just be 3x. Okay. Then you do the derivative of the y component of the force with respect to x. Okay. And when you take that differential, again you get a derivative of 3x. So, since both these are equal, you conclude that this is path independent. Path independent, and so what you would expect is that the work work done in going along path C1 should be the same as the work done in going along path C2. So, for this particular force, so for the first force, the work done in going along path C1 and work done in going along path C2 will be the same. So, what we saw is that the work done for the first force, for the first case of the force, the work done does not depend on which path you take. Okay. And for convenience, I will calculate this work using path C2. So, what do we know about path C2? So use path C2 to calculate work. So once again, just let us remind ourselves, you have x and you have y, x and y, and you have this point 1 0, and you have this point here minus 1 0, and the path C2 goes along the x axis this way. So, along C2, okay, y equal to 0. So, I can write integral or work is equal to integral from, and x goes from, so x goes from 1 to minus 1, and so dy is also 0. Okay. So the only term that will contribute will be the x component. So, that is, so now I will get 3xy minus 1 dx. Okay. But since y equal to 0, so I have 3 into x into 0 minus 1 dx. Okay. So, remember dy is 0, so I do not have any term involving dy. Okay. So, then I just get minus 1 dx. This is equal to integral minus 1 dx from 1 to minus 1. So, we are going from 1 to minus 1 in x. So, x is going from 1 to minus 1. So, this is equal to 2. Okay. So, that solves the first part, and you know, you can verify, it is a little more tedious, but you can verify that even if you take path C1, you will get the same answer. Okay. But I will not do that here, but in the second case of the force, okay, we will look at path C1. Okay. So, let us look at the second case. So, in the second case, we have the force given by minus x square j. Okay. Now you calculate dou Fx by dou y. Okay. So, if you take the derivative of this first term with respect to y, you just get x, and dou Fy by dou x, this is equal to minus 2x. Okay. So, clearly these two are not equal. So, this is path dependent. Okay. So, now let us use along path C2 to work done is equal to integral, again you will have 1 to minus 1, and you just have the x component times dx, but if you look at the x component, okay, so you have x into, now y is 0 as we saw in the last in the earlier part of the problem, okay, and you have dx. So, the work done is 0. So along this path C2 you do not do any work, and just to remind, you have C2 is the path going from 1 0 to minus 1 0 along the axis. C1 is the path going along the circle. Okay. So, the work done along path C2 equal to 0. So, what about the work done along path C1? Okay. So now you have to parameterize this path C1. So, in other words, you have to somehow write this path. So we have f of xy is equal to xy I minus x square j. Okay. Now, in this xy coordinates, this path is not easy to parameterize. Okay. So, what you have to do is to go to spherical polar coordinates, okay, and so you use, or in this case it is actually plane polar coordinates. Plane polar coordinates, what is done is you go from x and y to r and theta. So instead of having a point x y, you describe by r and theta, and you use x equal to r cos theta, y equal to r sin theta. Why does plane polar coordinates help? Along C1 r equal to 1 constant. So along this path your r does not change at all. So r is fixed at constant. So the only change is due to theta. Okay, and what you can do is you can write this integral now, and so you substitute for x, substitute for y, okay, and you also have to consider this. So if I write w is equal to integral xy dx plus integral, or minus in this case. So, there is a minus sign, there is a minus x square. So, I will put a minus sign. So, minus integral x square dy. Okay. This is along path C1. Okay. Now what I can use is that since x is r cos theta and r is fixed, okay, I can write dx is equal to sin theta d theta with a minus sign. So, minus sin theta d theta, and dy is equal to cos theta d theta. Okay. So, both dx and dy can be expressed in terms of theta, okay, and similarly I can express x and y in terms of theta, again r equal to 1. I am taking r equal to 1. So I can calculate the work, and I will get the expression, I will get it as an integral. Now theta along this path, so if you look at theta here, okay, theta goes from 0 to pi, okay, theta is defined to go from 0 to pi. So what you have is integral from 0 to pi. Now x times y is nothing but cos theta times sin theta. Okay, so it is cos theta times cos sin theta, and then you have a dx. So you will get another sin theta. So what you have is minus cos theta sin square theta, that comes from here, and the other term minus x square, that is x square will give you cos square theta, and dy will give you another cos theta. So, you have minus cos cube theta the whole thing d theta. And you can simplify this. In this case if I take cos theta outside, then I get sin square theta plus cos square theta. So, I get minus integral 0 to pi cos theta d theta. So, what is this value equal to? So, this is equal to, so integral of cos theta is sin theta. So, minus sin theta from 0 to pi, and this is equal to 0. So, the work done is actually 0. Okay. So, what you notice is that you got 0 work along both these paths C1 and C2, okay, even though your force was actually path dependent. Okay. So, the force is path dependent, but for these two paths, and I emphasize it is only these two paths that you got the same work done. Okay. So, in both these cases the work done was 0. Okay. So, that completes the first problem. Now, I will do the second problem. Okay. So, the second problem that I want to give, okay, that involves a volume integral. Okay. So, this involves a volume integral. Okay. So, here provided that the wave function of 2px orbital of hydrogen atom is given by psi of 2px. This is proportional to r e to the minus r by 2a into sin theta cos phi. Okay. Now, what you are asked to do is to calculate a volume integral, and that volume integral I will just calculate psi 2px square d cube r. So, overall space. Okay. So, you calculate the volume over the entire 3-dimensional space. Okay. So, I will just give you a little bit of background about this problem. So, I have expressed this wave function, okay, in terms of r, theta and phi. So, it is already expressed in spherical polar coordinates. So, I will just mention it here. So, we have used spherical polar coordinates. So, what are spherical polar coordinates? So, if you have a coordinate system where these are the axes x, y, z, okay, then if there is a point x, y, z are the coordinates of that point. Okay. So, instead of using x, y, z coordinates, you use different coordinates, you use spherical polar coordinates. So, where this is given by r, okay, r is the distance of the point from the origin, and then your theta is the angle that this r makes with the z axis, and phi is the angle that a projection of r onto the xy plane makes with the x axis. So, these three coordinates, they define what is the usual spherical polar coordinates. Now, what are the conversions used? So, you can use so r theta phi can be expressed in terms of x, y, z as follows. So, I can write x as r sin theta cosine of phi, y is expressed as r sin theta sine of phi, and z is expressed as r cosine theta. So, and the other thing that you need to know for this, okay, is that d cube r can be written as r square sin theta dr d theta d phi. So, it's so when you do a volume integral, you have a integral over 3 variables, okay, and you have a, so this is dr d theta d phi, but when you write d cube r is same as dx into dy into dz. So, this is equal to dx dy dz. Okay. When you convert it to spherical polar coordinates, then you do not just write dr d theta d phi, you have to have this factor of r square sin theta, you have to have a multiplicative factor of r square sin theta. So, with all this information we can easily go ahead and calculate this integral. Just little bit more information. So, the range of variables, so I will just, so 0 less than equal to r less than infinity, 0 less than equal to theta less than pi, 0 less than equal to phi less than 2 pi. So, these are the ranges of variables. So, if you want to span the entire space, these are the allowed values of r, theta and phi in the spherical polar coordinates. So, 0 less than r going to infinity, as r becomes larger, you go more and more outside, you go more and more further from the origin. Okay. So, with this information we can go ahead and calculate this integral. Okay. So, let's calculate integral psi square d cube r, and you might recall from your quantum mechanics course that this is what you need to calculate in order to find out the normalization constant for this wave function. Okay. So, now we can go ahead, we have all the information needed. So, let us just go ahead and calculate that integral. So, what we need to do is integral psi 2 px square d cube r. Okay. So, I will just over all space. So, let us just go and copy it down. So, you have r square e to the minus, so when you square this you will get r square e to the minus r by a0 r by a. So, you have r square e to the minus r by a. I will put the limits in a bit. So, r goes from 0 to infinity, theta goes from 0 to pi, and phi goes from 0 to 2 pi. Okay. Now, I just substituted one part and then I have a square of this. So, sin square theta cos square phi. So, times okay, and then I had a d cube r, here. So, the d cube r is given by r square sin theta dr d theta d phi. Okay. Now what you can do is you can separate the integral into 3 integrals. So, I will write, so you have 0 to 2 pi. So, 0 to 2 pi is the range for phi, for the variable phi, and the only function of phi is cos square phi. Okay. And then this will multiply an integral over theta which goes from 0 to pi, and now you have a sin square theta into sin theta. So, you have sin cube theta, and finally, you have an integral over r which goes from 0 to infinity. Okay. And what you have is r square into r square. So, that is r to the power 4, and you have e to the minus r by a dr. So, you have to do each of these integrals, you have to do each of these is a simple one dimensional integral. Okay. And you can do this easily and calculate the values. So, if you want to do cos square phi d phi, then you replace cos square phi by 1 plus cos 2 phi by 2. Okay. So, when you replace this by 1 plus cos 2 phi by 2, then you do the integral, you will get phi plus sine 2 phi Okay, so phi by 2 plus sine 2 phi by 4 integral, and you put the limits 0 to 2 pi. Okay, so that is this first part. The second part, the theta part, okay, that works out to, so sine cube theta. Okay, so if you replace sine cube theta in terms of sine theta and sine 3 theta, okay, and then you can do the integral. I'll just write the final answer for the integral. So you get minus 3 cos theta by 4 plus cos 3 theta by 12 integral from 0 to pi. Okay. And then this last integral, I will write it slightly differently. I will write this as integral. Now instead of my variable, instead of taking my variable as r, I will take my variable as r by a. I will just change my variable from just r to r by a, okay, and there is a reason for that. So I will write this as a raised to 5 times integral r by a raised to 4 e to the minus r by a d of r by a. Okay. So you can see that I have changed the variable of integration from r to r by a, but the limits do not change, because when r equal to 0, r by a equal to 0, when r equal to infinity, r by a equal to infinity. So this is my final expression, and you can substitute this. This will give you a factor of pi. This particular expression will give you a factor of 4 by 3. Okay, and finally this particular expression is a raised to 5, and then you have an integral that looks like x raised to 4 e to the minus x dx. You have an integral of this from 0 to infinity, and if you look up, this is related to something called a gamma function. This is essentially this is an integral representation of a factorial. Okay, so this is equal to 4 factorial. Okay, so finally what you get, you can write your expression as, so 4 factorial is 1 into 2 into 3 into 4. So if I cancel the 3, then I will get 1 into 2 into 4, that is 8 into 4 32. So I have 32 pi a raised to 5. Okay, so this is the final expression, and you got this by doing this volume integral. Okay, so we will start module 4 in the next class. Thank you.